Okay, so we're going to do work and energy. This is the most important physics chapter in your textbook. Okay, so this is the one that you need to really focus and well. So let's look at the concept, work and energy. Now, in the past, okay, let me just give you an equation. W equals F delta X cos theta. That's your first equation. And I'm going to quickly explain that. W is just work or energy. Work and energy is the same thing. So that's work or energy, and that's in joules. So you can think of that as work or energy. Same thing. And then F is just force. That's in Newton. And then delta X is distance. That's in meters. And then cos theta, I'll explain a bit. That is the angle between, that's angle between the direction of movement and the force. That's the angle between the direction that an object is moving and the force that you are applying. Okay, happy with that? Just quickly make a note of that. That's the first equation. There's other equations that we're going to learn, but that's just the first one we're going to learn. It's a quick, makes the chapter nice and easy. We start off really easy. It's always nice if you have your video on, then I can see when you're still writing and when you're not. Makes it easier for me and quick, makes the lesson more, we can do more because I can see if you're still writing or you just like finished. Okay, so imagine the following. Imagine I have a box or an object and it's lying on a surface. There's a kinetic friction or a frictional force of 50 newtons, and I'm applying a force of, let's make it 20 newtons, 20 newtons to the right. So this is my force. I'm applying a 20 Newton force on a brick with a frictional force of 15 newtons. Then they can ask you the following. It's a very easy example. What is the net work done? How much energy? What's the net energy applied? Or what's the netto work or net work? And that's called V net. What's the net work done? Okay, then you can do it. There's two ways to do this. You can say the net work is the work done by the applied force plus the work done by friction. Now look at the following. If I draw a free body diagram of all the forces on that box, I will have an applied force, I'll have a normal force, I'll have a gravitation force and a frictional force. Can you see that? Very important that you communicate with me.
Yes, sir.
So in effect, the truth is actually that the net force is the sum of, or the net work is the sum of all the work. So I have to add the work done by the normal force and I have to add the work done by the gravitational force. That's actually true. But because the movement or the direction of movement is in that, so it's moving in that direction, these two forces, the normal force and the gravitational force, makes a 90-degree angle with the movement. Can you see that? The angle between the direction of movement and those two forces are 90 degrees. Happy?
Yes, sir.
And the moment I multiply that force with the distance and cos the angle, and in this case 90 degrees, it becomes 0 because cos of 90 is 0. So I can ignore those two. I can ignore all the forces that has a 90-degree angle with the movement or the direction of movement. So I can just do those two. Do you understand? Because if I worked out the work done by the normal force, let's assume that we're we're pulling that 12 meters. That's the distance we're going to pull it. If you have to calculate the work done by the normal force, now work is force times distance times cos theta. So the normal force is what? It's just Fg, same as Fg, for 12 meters cos 90 degrees, and that's just 0. So it doesn't matter what it is, it will be 0. So we are going to ignore that. So the net work done is just the work done by the force applied plus the work done by friction. And look at the following, very important. We're not putting a sign in there like a negative or something. We're just keeping it plus. I'll show you now why. Okay, so now we have the applied force times the distance the force is applied, cos theta, plus we have the frictional force times the distance the frictional force is applied, cos theta. Okay, now look at the following. The applied force is 20 meters over a distance of 20 newtons over a distance of 12 meters, and cos 0 degrees because the angle between this force and the movement is 0 degrees. Can you see that, everyone?
Yeah.
Neil and Ria?
Yes, sir. I see.
The movement is in that direction. The force is exactly in the same direction, so there's no angle between it. The angle between it is 0. Plus the frictional force of 15 newtons over 12 meters cos. Now, look at this. The movement is to the right, and 180 degrees from that is the frictional force, so that's cos 180. And that, all that does, it just gives you a -1. So it just gives you direction. So you're not going to put a negative in there. It's wrong. Because that 180 degrees is going to give the sign. Now, all you're going to do is 20 times 12 minus 15 times 12. And that's just 60 joules. See if you get this. It's not a vector, so no direction, just joules. Energy is it's not a vector, scalar, so there's no direction. So the net work done is 60 joules. This is so easy. The chances of you getting something like this in exam is zilts, or very, very low. We're going to ramp it up. We're going to probably do 3 lessons on this. Happy? Everyone finished?
Yes, sir.
Look at another method. You could also have said the net work done is F net, the net force, delta x cos theta. Then you could have gone and work out the net force again. F net is what? Is the applied force plus minus the frictional force. And that would have been 20 minus 15, and that is 6 newtons to the right. That's your net force. Then you can put it in here, 6 times 12. And the net force is to the right. The movement is to the right. So that's cos 0 degrees. And that is also, this is a mistake. This is not 6, 5. No? Look at me, 6. So this is 5 times 12, and that's 60 joules. So you can also have done it this way. It's another way of doing it. Okay, happy? Yes. Quite easy.
Yes, sir.
Yes, sir. We are very happy.
Can I
So now
continue to the next?
which method works best, I guess?
So say that again.
I'm saying, so which method would you say works best? Like,
You're gonna the sums are gonna lean towards this method, but you must be aware of both.
okay.
There's some of the times that if I give you the acceleration, for instance, then you're gonna lean towards F net, because you can also calculate F net as m times a.
Okay.
That from Newton 2. Okay, anyway, this is still really easy. We're just gonna do another example that's on the same trend. So now I have a box or object, I'm going to give you the mass, but it's not going to be important now. Let's say it is 4 kilograms, and the frictional force is 12 newtons, and I'm going to be applying a force at an angle. Let's say this force is 25 newtons, and the angle is going to be 30 degrees. Okay, now, what is really important is as follows. You're not allowed, if they ask you to draw a free body diagram, the only one that you are allowed to draw is this one. Now, I'm not 100% sure if Impact has updated their memos yet, but according to the CAP syllabus, this is now the only way you're allowed to do it. You're not allowed to do X and Y components anymore. Remember, you used to do it like this. This is the better free body diagram. Remember, can you remember doing it like this? Putting your X and Y components in.
Yes, sir.
Okay, you can still do this, but do this on a loose paper that you're not going to hand in.
Okay.
So this is the red one is the one we used to do. You're not allowed to do that anymore. So now I want to know, what is the net work done? Okay, good. There's a couple of ways to do it. I'm going to show you method one. Method one is just say the net work is the work done by the applied force plus the work done by friction. I have now not used the normal, not included FG. Why? Simply because they are at 90 degrees with the direction of movement. Are you happy with that?
Yes, sir.
The object
Yes,
will
sir.
move in the direction of that dotted line. You're not allowed to put that dotted line in the free body diagram. I'm just showing you that. So the normal and the FG forces are at 90 degrees to the direction of movement, so we can cancel them. Okay, right. So the net work is, you have to write the equation like this. This is the applied force times the distance, cos theta, plus the frictional force times the distance, cos theta. Okay, now I haven't included the distance again. Let's say that we are going to be moving that for 100 meters. We're dragging that box 100 meters far. So now look at this. The applied force is 25 newtons. It's over a distance of 100 meters. Cos, the direction of movement is 30 degrees to the force, or the force is 30 degrees to the direction of movement. That angle is 30 degrees, so that's cos 30. See that? It's moving to the right, and the force is 30 degrees off that movement. And you know, in trigonometry, you always move anti-clockwise, always positive. No,
Yeah.
so that's a positive 30 degrees. Okay, awesome. Plus the frictional force over 100 meters. Now, the frictional force is at 180 degrees to the direction of movement. So that is cos 180, which just makes it -1. So in my calculator, I'm just going to type in 25 times 100 times cos 30, and then just minus 12 times 100, because cos 180 is just -1. Minus 12 times 100. Bang. And then I get 965,06 joules. Please write that down. I'm just going to move it a little. And then when you finish with this, I'm going to make it small. We're going to do another way. Another way of doing that. Just another way of reasoning. It's still not difficult.
We're done, sir.
Okay, Zelnay, also done?
Also done.
Okay, awesome. I just want to show you something else. You can also reason as follow. Just going to do it in red because it represents the red diagram. You can say the net work is the work done by the x component, or you can use fx if you want to, plus the work done by friction. Now the x component, if you can remember, the x component is the force cos alpha. No,
Yeah.
delta x, because that's the distance, cos theta. But this becomes really difficult now. Can you see that? We don't like that. No. Because I've just converted the fx component into f cos alpha. Alpha is now that 30-degree angle. Just focus. Plus the frictional force, delta x cos theta. Okay, now, the applied force is 25 newtons. Cos alpha, which is 30 degrees. Okay, so I'm going to put that in brackets. The distance we're pulling it is 100 meters. And then look at the following. If I've used the x component here, the x component and the direction of movement is exactly the same, then I will have cos 0 degrees there. Can you see that? Because the x component of that force is exactly in line or parallel to the direction of movement. Then it is a 0 there. Plus the frictional force, which is 12 times 100 meters cos 180. Now look at this. It's exactly the same as the previous one. There's a 25, 100, a cos 30. A 25, 100, a cos 30. So the answer is going to be exactly the same. You see that? It's just difficult, this one. This is if you still use the x component in a free body diagram. So this is another way of reasoning. I will stick to the first one. Looks easier. It doesn't matter. It doesn't matter which one you prefer. They're both the same. Can you tell me when you're ready? It's going to make this look neater. Cos 180.
We're done, sir.
Did you understand what I've just done?
Yes.
Zelno? So this was the fx component. It's F, the applied force cos the angle. Okay, so now we've done two flat surfaces. Let's move towards a sloped surface. So let's assume that I have a 20-degree angle here. And I have like a box or something. No, let me draw it like this. Make the slope a bit longer. Let's make a box there. Trying to make the box level on that. Is that good enough? Yes. Okay, let's give this box a 5 kg mass. And let's say that the friction here is 8 Newton. And then the distance here is 20 meters. Okay, so I've got a box. It's at rest at the moment. Let's say the velocity is 0. It's just lying there. And if I stop touching it, or stop, just leave it, it's going to slide down that slope. I just want to change one of the stuff. 20 meters and 20 degrees is a little bit ambiguous. So let's just say it's actually just sliding down 10 meters. So the distance is going to slide down is 10 meters. And it's at a 20-degree angle. Let's quickly just draw a free body diagram of all the forces. So we agree that there's a normal force, then there's friction in that direction, and then there's a FG component there. Happy with that? Again, this is the only diagram that's going to be marked correct in a CAP syllabus. But I know that you are writing, impacts exam in June, so I'm not sure if they updated on that. But this is supposed to be the only one that's marked correctly. The next one is the one that you used to work with. You took the FG component and you made a parallel and a perpendicular component out of that. Is that correct?
Yeah.
Okay, so I would still recommend drawing this somewhere on a loose sheet of paper. So when you write the exam, you get like loose paper to work with to do rough work on. Draw that on your rough work. You're not allowed to draw that on your exam paper. So quickly make those two drawings and then make a note that this is the correct one. Use this one or use this in answer if they ask you for a free body diagram. Now, this is a very important example because there's 3 ways of doing this. We're going to use the purple one first. Focusing on that. Tell me when you're ready.
And then so
Ready, sir.
Right, so we're still asking the same question. What is the network? The reason we're doing this is because this is going to be an important question to actually answer the question that they want to answer. The question that they want to answer is what is the velocity at the bottom? But we're not doing that today. We'll be moving into that next week because there's 2 other equations that you have to learn before we can do that. But the first thing is, what is the net work done by gravity or just work done on the block? Okay, so the net work, I'm going to use this diagram, is the work done by the parallel component plus the work done by friction. Can you see that the actual block will just slide down in that direction? So this is my direction of movement, and the normal and the FG perpendicular forces, these two, they are just perpendicular to that movement, so I can just ignore them. Happy with that? Understand that? Okay, so now the net work is the work done by the parallel force. Now the parallel force is what? Is FG parallel times the distance cos theta plus the work done by friction is the frictional force delta x cos theta. Now the parallel force is mg sin alpha. That's this. You don't have to write this down now. You can just look what I'm doing and I'll give you some time to write it down. So that's mg sin theta. The distance is 10 meters and then cos 0 degrees because the parallel component is there's a 0 degree angle between the direction of movement and the parallel component. Then we have plus the frictional force, which is 8 newtons over a distance of 10 meters, cos 180, because there's a 180 degree angle between the direction of movement and the frictional force. So the mass is 9.8 sin 20. This I'm going to multiply with 10 and 1. Cos 0 is just 1. And this is going to be minus 8 times 10 times minus 1, so that's minus 80. So let's put that in a calculator. Just do your brackets correct. I get 87.59. joules. If you use 3 decimals, it's going to be, yeah, 950. So see if you get that answer, and please write that down. Just going to mute myself for 10 seconds. Okay, Zalnaya, are you finished? And Neil and
Yes, I was
Yes,
done.
sir, we finished.
okay. Okay, that's one way of doing it. And I'm just going to group this together because this is the way you're going to probably be doing it if you're using that purple diagram. Okay, now if you're using this green diagram, now you have to focus. Then there's two ways of doing it. Now, look at this. You can say V net is the work done by gravitation plus the work done by friction. Again, the direction of movement is that direction. That's the direction of movement. And this normal force is at 90 degrees with that. So I'm going to ignore that, which leaves the two other forces remaining, the FG1 and the F. Now we have a small problem. The angle between FG and the direction of movement is quite difficult to get. Can you see that?
Yeah.
So we're not going to use that angle. Now I'm going to teach you something very important. We're going to come back to this, but I just want to show you something really important. Imagine the following. Okay, don't want to use a dotted line. Imagine the following. That represents like a slippery slide or a slope that you can slide down. And this is the ground, this dotted line. Now, let's assume there's two of you, person A and person B. Now, person A can actually just slide down here, while person B jumps down. Both of them are going to get to the ground. Do you agree? Yes. The one's going to have a longer journey. A is going to go a longer distance. B is going to go a shorter distance. But let's say this is the work done by the parallel force, and let's say this is the work done by gravitation. The work done by the parallel force is exactly the same as the work done by gravitation. That is really important. In other words, the Earth is going to do the same work on person A by making him slide down compared to person B, which jumps down. I know if there's friction, the velocity of A is going to differ from the velocity of B. Think about that. The velocity is going to differ. Why? Because some of the energy is going to be absorbed by friction. Okay, so if you jump down your roof, you're going to hit the ground at a higher velocity than sliding down. But that's got nothing to do with the work that the Earth does on you. The Earth is doing the same work on both. So instead, of making the person slide down, you can just make him jump down and you'll have the same energy. So we're going to use this, very important. We're going to re-look at this over and over again. So let's look at following. So I don't want to use this difficult angle here. Can you see that?
Yes, sir.
So I'm going to say, let's just take that block and drop it down and then I'm going to use this FG component. In other words, I'm going to force it down in this direction, make it fall down in that direction. Okay. So now let's just make a little triangle to get a new value that we don't have yet. If that's the triangle and I drop it down in that direction, and this is 20 degrees and this is 10 meters, I can calculate that height. No. Sin 20 is opposite over hypotenuse. So h is 10 sin 20. Is that correct? Everyone agrees.
Yeah.
The height,
You said 20 is opposite over hypotenuse.
yeah, that's sin. Sin is
Oh,
opposite
you
over
know-
hypotenuse.
I see, sir, because I just automatically assumed that the H was for hypotenuse.
Oh,
That's what I'm like,
the H is the H is for height.
yeah.
Okay, sorry about that. I get it. So the height that we're gonna make it fall down is 3,4202 meters. Okay, so now look at this equation. V net is Fg times the distance cos theta plus the frictional force delta x cos theta. So the Fg component is mg. Now, if I make it fall straight down, it's only going to fall a distance of 3,4202 meters. And then the direction of movement is down. The block is moving straight down and the force is down. So that is cos 0 degrees. Very important. If I'm making it fall straight down, the movement is straight down and the force is straight down. So there's no angle between the movement and the force. And then plus the frictional force. Now the direction of the frictional force is this direction. Or the block is moving that direction if it encounters friction. So the frictional force is 8 newtons. The distance is now 10 meters. Cos 20. Okay, mg is 5 times 9,8 times 3,4202, and cos 0 is just 1, and that's plus, sorry, this is a lie. This is not 20 degrees. 180. Remember, the frictional force is 180 degrees to the direction of movement. So that's just minus 80. Can you see both has got the same values again? Type that in. So I'm keeping that answer. I'm just timesing it with 9.8 and 5. And then I'm subtracting 80. If I put that in my calculator, I get 87,59 joules. Same answer. So this is method 2. And this was method 1. Method 3, I'm not going to show you. Because method 3 uses this funny angle, which we're never going to calculate. Okay. Which is going to be, I think, 290. Yeah. Yeah. Do you want me to show you that method? Yeah, why not? We have time. You can just ignore it. Because I think it's the worst method or the most difficult one, but some schools do teach it. Are you happy with this? Look, I never want to confuse you by showing you more than one
Yes, sir.
method. It's the plan is always to show you alternative ways of doing it. There is a reason why I had to show you the green method. Look at this. If my slope looks like this, you see this, and there's the box, then it is not possible to calculate this distance. then you have to throw the box down in that direction. Then you have to use the green method. You see? Hello.
Yes, sir.
Okay, last
Yes, sir.
method. And then we finish for the day. You're going to make this blue. Method 3. And I'm going to draw a little face like that, because that's not some very few students like this method. Okay, I'm going to go and make the direction of movement there again. That's my direction of movement. And now I'm going to say V net is the work done by the gravitational component plus the work done by friction. So the net work is Fg, that's the gravitational force, times the distance cos theta plus the frictional force delta x cos theta. Now I'm going to use this angle here. Why? That's the angle between the direction of movement and the Fg component. Huh. Okay, so V net is Fg, which is mg, and then the distance going to be 10 meters because I'm sliding it down, and then I have cos. Now, look at this. If I complete this triangle here with a 20 degrees there, this will be 70 degrees if that is 90. Do you agree? Let's just focus again on that. This is 90 degrees. This angle was 20 degrees and this is 70 now.
Yeah.
So that blue angle is 360 minus 70, which gives me 290 degrees. No,
Yes, sir.
it's actually minus 290, but I'm just going to put 290 degrees there. Plus the frictional force, which is 8, distance 10, cos 180. Okay, now we're supposed to get the same answer. Let's look at this. The mass is 5, 9,8 times 10, and then cos 290 is what? It's just 0,3420, and this is minus 80. So I'm going to multiply it with 10, that 0,34. I'm going to multiply it with 9.8 and 5, and then I'm going to subtract 80, and then I get 87,59 joules. Bang, same answer. Do you like this? No.
Yes, sir. No, no.
Look, I would recommend the green method or the purple one.
Okay, sir.
Don't use that funny angle, okay? It's very difficult, actually. You must be able to use the green one and the purple one. Okay, so once you finish with this, you tell me. Then I'm going to give you one example that we're going to try on our own.
I'm done, sir.
Okay, there's a slope. Let's make an easy angle here. 30 degrees. Then I have a box at the bottom. I'm going to try and make a box there. Oh, yeah, it works. Is that good enough?
Yeah.
Yes, sir.
A red box. Let's say the mass is 10 kgs. And the average friction is 20 newtons. That's the frictional force between the surface and the box. So I'm pulling it up with another force. I want you to draw a free body diagram of all the forces on the red box after you've made that drawing. There's not a lot you can do yet in this chapter, okay? We're just doing all the prep work to get the network. The network is the key to getting the velocity of the object.
Okay, sir.
So this takes at least 2 lessons to get this chapter going. I would recommend doing the Doppler effect in between. So make sure that you understand what we've done today, and then complete the Doppler effect, and then next week we do the velocity calculations, and then we can do all the stuff. So that's the free body diagram of all the forces on the box. Okay,
Okay.
happy with that?
Yes, sir.
Right, so now I want to know, what is W net? What's the network? Okay, I'm going to do the following. I'm going to say the network is the work. It's the work done by the applied force plus the work done by friction plus the work done by the gravitational component. You see that? You can have Fg here. Doesn't matter. I just use G. Okay. Right, because G qualifies for Fg and Fg parallel. That's both of them are called G. So it's like a safe way of writing it. Okay, now help me out. Let's say I'm only pulling it up 5 meters. So the distance we're pulling it, it's 5 meters. Okay, so the net work is the work done by the applied force. So that's the applied force, the distance cos theta, plus the work done by friction is the frictional force, delta x cos theta, plus the work done by gravitation, which is the gravitational force, delta x cos theta. Okay, I had to actually give you that force, otherwise you can't do it. So let's say that is 40 newtons. So the net work is the work done by the applied force over a distance, which is 40 newtons over 5 meters. Cos, can you give me an angle there, please? Which direction is this box moving? Let's say it's moving up. So the direction of movement is this pink line. Do you agree?
Yes, sir.
So there's a 0 degree between that force and the movement. The frictional force is 20 over a distance of 5 meters. Zelnay, can you give me an angle there?
Will this be for the frictional force, which would it now be 30 degrees, or would we say it would still be 0?
Look at this. There's the movement, and the angle between the movement and the frictional force is 180 degrees. See that?
Okay.
Yeah.
And then Fg is mg for a distance. Okay, now we have to make a big decision here. Do we want to use, look at this, do we want to use that crazy method, which implies we're going to use that angle? No. See that? So you can either use one of the 2 methods we've done. You can say, look, let's just get this distance. Let's just pull it up that distance, because that is just opposite direction. Or you can say, I will prefer using Fg parallel. In other words, I would have loved to draw my free body diagram like this. Some of you will prefer this. Why? Because this is where you do your Newton stuff. Fg perpendicular, and then this is Fg parallel, isn't it?
Yeah.
Maybe this is the best method for you. So I'm gonna do the following. I'm gonna take that Fg component, I'm just going to make a little bit more space here for myself. I'm going to take that component and say that is not just mg, that's fg parallel. I'm going to write this in purple, which means mg sin alpha. That's fg parallel. And then that distance is going to be 5 meters. Cos 180. Look, this is direction of movement. And then that FG parallel is 180 to that. So here at the beginning, we'll just have 200 minus 100, because that 40 times 5 is 200. And 5 times 20 is 100, times minus 1 is minus 100, plus m times g sin 30 times the distance of 5 meters and minus 1. Okay, so that you need to put in your calculator. 200 minus 100 plus 10 times 9.8 times sin 30, which is 0.5 times minus 5. And then I get, oh my word, we're not pulling this up. 40 newtons is not big enough, strong enough. Really? Sorry about that. Let's just change that 40 newtons to 70 newtons. And this is 350 then. Really? I didn't know that. And that's exactly 5 joules. The frictional force was a lot, that's why. So the net work is 5 joules. We're just barely pulling that thing up. Do not be too worried about this. We are going to do more and more of these examples. The next step is to calculate the velocity on top there after 5 meters. And then we have to do everything we've just done again to get there. So what I'm doing, I will load this